So I am stating a lemma on minimal polynomial, based on which we will be doing your main theorems of unit 2. So one is, first is, you say MT is minimal polynomial for linear operator phi, and FT is any other polynomial, and FT is any other polynomial, any other polynomial satisfying is any other polynomial satisfying phi, then MT will divide FT. So this is first theorem, and second is primary decomposition theorem. You must have done this in your unit 1. So theorem says primary decomposition theorem, primary decomposition theorem. It says that let phi be a linear operator on capital B. Then let MT is equal to something like F1t power n1, then F2t power n2, so on, Fkt power nk be its minimal polynomial, minimal polynomial of phi, I mean. Then V is direct sum of invariant spaces W1, W2 up to so on Wk. These all are capital W1, capital W2, capital Wk, where Wi is what? Wi is kernel of Fi raised to the power ni. Okay, for all I. So you say i.e. vector space capital V is direct sum of Wi, where Wi is this, or you can directly write that this is kernel of Fi phi power ni, I from 1 to k. Obviously we need not write I from 1 to k here, we know this, or you can simply change the notation also. You say direct sum of summation I from 1 to k. This is also fine. So this is primary decomposition theorem. These theorems belongs to unit 1 of your syllabus. We are doing unit 2, and this is an invariant subspaces. Your topic is invariant subspaces. This is last topic of unit 1, you know this. Now I will state one theorem which I need to prove. So theorem says that what we are doing, if you remember, we are doing diagonalizable linear operators. Okay, so you say a linear operator phi is diagonalizable if and only if. Okay, a linear operator phi is diagonalizable if and only if its minimal polynomial is product of if and only if its minimal polynomial is product of distinct linear factors, is product of distinct linear factors. This is your theorem, and the result is in if and only if terms. Now how we will start the theorem? We say that proof given phi from V to V is diagonalizable. First is this is diagonalizable. If this is diagonalizable, then by last theorem we did, it says then by lemma phi has then by lemma V has a basis which is made of which consists of which consists of eigenvectors of eigenvectors of phi which consists of eigenvectors of phi. So you say let v1 v2 up to so on vn be basis of capital V made of made of made of eigenvectors of phi. Fine, easy. And let lambda 1 lambda 2 up to so on lambda n be corresponding eigen values. Then what? Then by definition, obviously, then by definition phi vi is equal to lambda I vi for all I from 1 to n. Fine. So you say implies phi minus lambda I into vi is equal to 0 for all I from 1 to n. I hope this thing is clear to you. Now what I am doing is I say make a linear operator or define a linear operator phi minus lambda 1 phi minus lambda 2 so on phi minus lambda n from V to V. Now what will you do is you say that phi minus lambda 1 phi minus lambda 2 up to so on phi minus lambda n if you put vi in it, if you put v1 in it, this v1 will meet this thing and it will become 0. If it meet v2, then it will come here and it will become 0. v3 next term it will become 0. So what I am saying is this thing into vi is equal to 0 for all I from 1 to n. i.e. what? i.e. t minus lambda 1, t minus lambda 2 up to so on t minus lambda n is a polynomial. Okay, t minus lambda 2 up to so on t minus lambda n is a polynomial satisfying what? Satisfying phi. And you have, see, this is lemma, so you say this is lemma 1. Okay, then minimal polynomial. Okay, minimal polynomial, any other polynomial, and any other polynomial, if it satisfies phi, then it divides empty also, then it is divisible by empty, also. So here you have, this is your polynomial and it satisfies phi. So by this lemma, therefore empty divides this polynomial t minus lambda 1, t minus lambda 2, t minus lambda, and I hope this thing is clear to everyone. This is very easy. Okay, now what we want to prove, we have taken that phi is diagonalizable. Fine. We want to prove that minimal polynomial consists of product of distinct linear factors. So you say this is empty These are all distinct factors. So empty is a part of this. It will be having obviously distinct factor implies empty is product of is product of distinct linear factors. I hope this thing is clear to you. Now we have to do the reverse part. Let me rub this. So this is our lemma, we need this. This is statement, we need this. This is first part, we need this. We have only this much space for converse part, but converse part is very small. So converse given what? Given minimal polynomial is product of distinct linear factors. Fine. Given minimal polynomial is product of distinct linear factors. Fine. Let empty is equal to t minus lambda 1, t minus lambda 2 up to so on, t minus lambda r. Okay. Now let's see this. This is a linear operator. Fine. This is minimal polynomial. Fine. Minimal polynomial is this. Then V is direct sum of so and so and so and so and so. So you say that by primary decomposition theorem, you can say this is your lemma. Okay, and it depends on, obviously you know this since you are in 4th semester, you know this. When a theorem appears in front of you, you have to decide how many lemmas will you prove. If it is 8-mark theorem, then you can prove only one lemma. For example, this lemma is sufficient, no need to prove any other lemma. Or if it is a 8-mark theorem and you don't know this lemma, then you prove one lemma. For example, this lemma, this is very short. So if you prove this lemma, then prove one more lemma if you are having that lemma. Okay. So you say then by primary decomposition theorem, this V is direct sum of kernel of phi minus f of phi minus lambda I. I hope this thing is clear to you. This thing is very easy. Okay. So you have this. What we need to prove? We need to prove that this is diagonalizable. If we want to prove this is diagonalizable, we need to prove that there exists a basis which consists of eigenvalues of your vector of your linear operator. Okay. So you say that you have what you have okay, Vi belonging to kernel of phi minus lambda I implies phi kernel. What is the meaning of kernel? Kernel means when you put this V in this, excuse me for a second. So definition of kernel says that when you put this element in the linear operator, this will become 0. This means phi V is equal to lambda IV. I hope this thing is clear to you. So what I am trying to say is, see, whenever you take one element from this lambda 1, it will give V, and this V will become eigenvector. V is eigenvector of phi corresponding to eigenvalue lambda I. We denote it by Vi, say. Okay, now what I am trying to say is I will make a diagram for you so that there is some clarity of concept. So this is your vector space. This vector space is made of k components. Okay, what is the meaning of direction? Direction is this vector space is sum of these components, and these components do not have anything in common except 0. This is the this is the meaning of direction. You know this. Now this is your kernel phi minus lambda 1 I. You take one element from this, you put this element in this, it becomes phi v is equal to lambda 1. What I am trying to say is this v, this is element of this subspace, this becomes its eigenvalue. In the same way, this is your kernel of phi minus lambda 2 I. You see, if you take element from this will become eigenvalue. Sorry, this will become eigenvector corresponding to eigenvalue lambda 2. So represent by v2, represent this by v1, represent this by v3, up to so on, represent this by vk. So you have one element each from each component of this vector space. And obviously, when you take elements from distinct components, these elements are surely linearly independent. These are all basic properties of direction. So when you combine these v1, v2, v3 up to so on vk, this becomes what? This becomes basis of a vector space. So we combine them. It becomes basis of vector space which are all eigenvectors of phi. So what is the meaning of this thing? You have derived a basis of vector space capital V, v1, v2, v3 up to vk. These all are made up of, these all combined, when they are combined they become basis of vector space. At the same time they are eigenvector of the phi of this linear operator phi. So what I am trying to say is you get a basis containing eigenvectors of phi. Hence, by lemma, this phi is diagonalizable, because lemma says if you have a basis containing eigenvectors of phi, then that linear operator becomes diagonalizable. So you have derived a basis v1, v2 up to so on vk. These all, first of all, they become basis. Second, they are eigenvectors. Hence, this phi by lemma becomes diagonalizable. I hope this is clear to you.